All right, good afternoon. It's day 2 of our States of Matter and the Gas Laws unit, Unit 6 for Chemistry B. Let's get started. Today we're going to talk about nature of liquids. Yesterday, or the last note guide, we talked about the nature of gases. We're going to talk about natures of liquids today. There is some similarities between liquids and gases. We'll start off by talking about one of those similarities, and that is what causes liquids to conform to the shape of their container. Gases do this as well. So you pour a liquid into a coffee mug, and that liquid will take the shape of a coffee mug. If you pour it into the shape of a styrofoam cup, it will take the shape of the styrofoam cup. If you pour it onto the floor, it takes the shape of the floor. What causes this? This is caused by their ability to flow, liquids' ability to flow. All right. There is a key difference, though, between liquids and gases. Even though they both have the ability to flow, there's a key difference, and that is the attraction between particles. In a gas, there is basically no attraction between the particles, but there is an attraction between the particles in a liquid. And this does keep these particles close together. So in a gas, those particles drift away from each other. That allows for smell to travel, or odors to travel, so we can smell them. But in a liquid, those particles are held together much closer because there is an attraction. Okay? The physical properties of a liquid are determined by the interaction of the colliding motions of the particles and the attractions amongst the particles. Liquids are also denser than gases because the forces reduce the amount of space between the particles. That should make some sense. If they're attracted to each other, they're going to be closer to each other. If they're closer to each other, there's not going to be as much room in between each of the particles. Therefore, they would be denser. Now, when we start to talk about behaviors of liquids and gases, and I know we're talking about liquids now, we want to talk about what happens when a liquid goes from being a liquid to a gas, and that's called vaporization. So I'm going to show you this right now.
Welcome back to Chem with Bill. Today we're going to take a look at these 3 vocabulary words and identify which one is the actual phase change. Well, if we look at the 3 things, and it's easy to mistake all 3 of these as the phase change to go from liquid to gas. But if we take a look at it a little bit more closely, boiling, is when the vapor pressure of a liquid has surpassed the actual atmospheric pressure that's pushing down on it. So if you remember from one of our demonstrations, at a vacuum pump, and we put a beaker that had some water inside of it, and we evacuated all the air inside of it. And in fact, by evacuating all the air around it, that made the pressure of the vapor for the water much higher than the atmospheric pressure that was pushing down into it, which caused this to actually start to boil. So boiling is not a phase change because it's just the increase or the decrease of the atmospheric pressure around the liquid in order for the vapor pressure to overcome the atmospheric pressure and then start to turn into the gaseous state. Now, if we take a look at the next vocabulary word, evaporation. Evaporation happens because particles on the surface of a liquid are exposed to wind particles that are moving a little bit faster. And at some point, what happens is at the surface of the liquid, these particles on the surface get picked up by these wind particles as they're traveling through this way, and those particles move into the gaseous state. And because there is a sort of space that's opened up right about there where that particle had left, another water particle can come in here and take its place. Now note that there is no addition of energy in this case. I mean, we could talk about the particles over here on the surface just turning into the gaseous state, but really there wasn't any energy added to any one of those particles. So, in essence, the true phase change from liquid to gas is vaporization. And the reason why is because energy was added to the system. All right, and that's it. Thanks for listening, and I'll see you in the next lecture.
All right, so that was a little bit about vaporization and gas and all that jazz, a little bit more than what we're going to talk about, but it gives you a good indication, okay? So a conversion from liquid to gas is called vaporization. When this conversion takes place minus the boiling, we call it evaporation. Why is it evaporation? Because the molecules in the liquid do not, that should say do not have enough kinetic energy to break the tractor beam and escape. They are held in that place. They get a little bit of energy, but they can't pull away from the other particles. They don't have enough kinetic energy to pull away from the other particles in the liquid. But the ones that are on the top or the surface, they do have enough kinetic energy to pull away, and they end up doing so, and that is why evaporation takes place. What is vapor pressure? Vapor pressure is when a semi-filled later container of liquid is sealed, some of the particles at the surface actually vaporize. The particles that vaporize collide with the walls of the container, making vapor pressure. So when you open a can of soda, for example, or open a can of pickles, and you hear that noise, that familiar when you open it, it is caused by vapor pressure. Excuse me. All right, that is caused by the particles that have vaporized colliding with the walls of the container, making that pressure. All right. Now, liquid evaporates into vapor. All right. Well, what happens when vapor wants to go back to being a liquid? It condensates. So we have liquid evaporating into vapor and vapor condensating into liquids. In a system at constant vapor pressure, an equilibrium exists between the vapor and the liquid. So as long as it is at constant vapor pressure, there will be equilibrium between the vapor and the liquid. The rate of condensation at that point is the same as the rate of evaporation, and that is what takes place with the vapor pressure. So liquid is evaporating into a vapor, and that vapor condensates back into a liquid. This takes place at a constant pressure, and that is equilibrium. In other words, it's taking place at the same rate. All right. Now, vapor pressure and the effects of temperature change. So as temperature increases, we know that vapor pressure increases as well. Well, why is this? Well, you should know this. That happens because these particles have increased kinetic energy. When you increase the temperature of the particles, they start moving around faster. When they start moving around faster, they cause increased pressure because they're colliding more. All right? And we measure vapor pressure in a liquid with a manometer, and you can take a look at that in your book on page 393. There's a picture of a manometer. All right. We talk about boiling point. Boiling point is when a liquid is heated to a temperature at which the particles throughout have enough kinetic energy to vaporize. That's when we will get boiling liquid. So in vaporization, in evaporation, we get the vaporization taking place at the surface because that is where the water has reached the achievable kinetic energy to break away. Well, when you're boiling water, or any liquid for that matter, when you're boiling it, you are applying that heat through the entire system, so all of the particles will achieve enough energy to vaporize, and that's when you get liquid boiling. Now, the technical definition of boiling point is when the vapor pressure of the liquid is just equal to the external pressure on the liquid. So boiling point is not only relies on how much energy you can give the water or the liquid. It also deals with what the pressure is of the area around it. We will do a demonstration where I will boil water at a much lower temperature than 100 degrees because I will also manipulate the pressure inside the container. We'll do that a little bit as well. All right. So because boiling point is when external and vapor pressure are equal, liquids do not always boil at the same temperature. Altitudes will affect this because of more or less pressure. So you can go to Colorado and you will boil water at a much lower temperature than you will boil it here in Farwell. Now here in Farwell we will boil it at about 96, 97, 98, depending on the accuracy of the thermometer. But it is not due to the fact that the thermometer is not working correctly. It is due to the fact that we are not at sea level. At sea level is where water will boil at 100 degrees Celsius. Farwell's at about 1,000 feet, and since it's at about 1,000 feet, it will boil at a little bit less than 100. As you go up in altitude, it will require less energy to boil the water. Okay? Atmospheric pressure is lower at higher altitudes, boiling point decreases, opposite true for lower altitudes. Less external pressure, the boiling point decreases, higher external pressure, the boiling point increases. The temperature of boiling liquid does not raise above the boiling point, it just boils faster. The bubbles in the liquid are not anything other than vapor. Okay, normal boiling point of a liquid is at a pressure of 101.3 kilopascals, and as you know, water's normal boiling point is 100 degrees Celsius.